most of what I'm talking about today I'll be presenting without any PowerPoint slides. I'm going to be using my tablet PC pretty much like a chalkboard in a real classroom. So what are we going to talk about this week? The focus this week is on noise and filtering. Very basic. And now I'd like to get down in the trenches a little bit and talk about some fundamental issues about noise and filtering effects, which of course are present in all communication systems and all optical communication systems. And we'll just be giving you some formality, some discussion about what exactly is going on behind all these simulations. So we're going to try and tie together the theory and the simulators. And very, very important is what we're going to talk about today is validation. So we're going to start by giving you some theory. So to take theory and use it to validate. So we turn to numerical simulations because our theory is not enough. Our theory cannot describe everything. And there are certain effects that we, instead of using theoretical analysis, have to do numerical analysis. However, the theory is still valid in certain regimes of operation. So when you're writing code, one way of validating is to reduce the operating parameters for your simulator into areas where theory should be accurate, and to see if your simulator does give you what theory tells you. So this is sort of the theme of the homework for this week, and the thread that will be carrying us through the noise and filtering. We should see what the theory tells us, and then we'll see how it might diverge from that as different effects. In the theory, we'll be developing equations, and there'll be many simplifying assumptions. And when we violate some of these simplifying assumptions, we expect that the numerical simulation will be giving us results that are different from the theory. And so we hope to see these effects as we're talking about it. So when we're talking about noise and filtering, we're also going to be taking the theory and letting us predict performance. And of course, when we talk about performance in a digital communication system, there's really one key figure of merit above all others that tells us about the performance of our system, and that is the bit error rate. So we'll be focusing a lot on how to calculate the bit error rate for a system, known of course as BER. Typically we'll plot this versus many different parameters. There are of course many other figures of merit of interest: spectral efficiency, throughput, many network criteria. But for today, for this week, we'll be concentrating on bit error rate. So in particular, in the first half of this week, I'll be talking about the theory, the sources of noise, the modeling of noise, how we take these models into simulations. And then the second half on Thursday will be more on filtering. So in terms of noise, which noises are we talking about? So today the focus is on noise. And on noise, we're going to be talking about thermal noise. We're going to be talking about shot noise. And we're going to be talking about amplified spontaneous emission. These are all additive noises, and in fact these three will be modeled universally as additive white Gaussian noise. So that's one of our first simplifying assumptions. However, it's a very good assumption for most of the regimes of interest in typical optical communication systems. So the thermal noise is let's say the thermal noise is very common in all systems using electrical detection have thermal noise. So any detection circuit is going to be characterized having thermal noise, so this is very similar to what we see in any classical digital communication source. Shot noise is found in various communication systems, but most importantly for optical communication systems, it comes from PIN photodetector. So these two sources of noise, both the thermal noise and the shot noise, are characteristics of photodetectors. We'll be focusing on the PIN. We won't be looking at APN. You can certainly find out theory about these and others, but the basic concepts are the same and the simulation aspects are similar, so we'll be just focusing on the PIN. Amplified spontaneous emission is created during when using optical amplifiers. Almost all systems involve some form of optical amplification, whether it's by using an EDFA, an erbium doped fiber amplifier, or using an SOA, a semiconductor optical amplifier. Both of these devices will be introducing a form of noise which is very wideband. It's called ASE noise, or amplified spontaneous emission. So that will be the focus of today's lecture. And we'd like to know how we can characterize these noises and use them to create a theoretical prediction of the bit error rate. Of course, there are other noise sources which we will not be talking about today. So not up for discussion today would be like crosstalk, which is interference across channels. For sure we'll be talking about filtering effects, and the reasons that we have filtering effects is trying to avoid crosstalk. So although we won't be characterizing it, we will be discussing issues related to crosstalk. There's also I'll say intersymbol interference, which we can think of as I guess we can think of it as a noise source, we can think of it as a distortion, but I'd like to think of it as a noise source. So these two issues are related to filtering. And so although we're not going to be predicting BER based on the level of crosstalk, although there's certainly results for that, what we're going to be focusing on is filtering, and that filtering is used to avoid these. So I'll introduce the topic on Thursday with some discussion about when intersymbol interference comes in, what are typical ways of avoiding it, and so on Thursday, when we get to the second half on filtering, we'll be talking a little bit about pulse shaping, and ISI avoidance. And pulse shaping can also be used to reduce crosstalk to allow tightly spaced channels. So they're all interrelated. So those are the big lines of what we'll be covering this week. Then I'd like to go ahead and start now with the first half of the topics for this week, which is dealing with noise and BER prediction. And of course, I said that the noise sources that we're going to be used are additive white Gaussian noise, which is going to make our BER calculation feasible. The theory for this being relatively straightforward to apply. So a PIN is basically a square law device. Whatever signal is input, whether it's constant or it's time varying, we'll see its field squared during the optical electrical conversion, a square law device. So some signal in to a PIN, what comes out is proportional to the signal squared. However, it's not just the signal squared that comes out. There are also noise sources. I just want to mention that depending on the setup you use, you may have several photodetectors. For instance, coherent detection, you'll use balanced photodetector. There'll be other components. This will be covered mostly in later weeks, so now I'm just going to focus on a single photodetector so we can get the basics down. So in addition to an electrical signal which is proportional to the square of the input signal, the pin adds noise, and one source of noise I mentioned is the thermal noise. And again, this is thermal noise, which we find in all electrical receivers. It's the classical additive white Gaussian noise that's modeled as a flat power spectral density. Okay, and it has a Gaussian distribution. It's flat, which is where we get the name, the acronym AWGN. The level of the power spectral density, we'll call in the noise level for thermal power, is given by the classical thermal noise, which is 2 times the Boltzmann constant, temperature divided by the load resistance. And the power spectral density, which I'll call S thermal, as a function of F, is constant for all F. Of course, no device has infinite bandwidth. In fact, the F, I guess we could say, for all F within the bandwidth of the PIN. Certainly we can say that the thermal noise is very well now modeled as flat over this bandwidth. In fact, that's sort of the definition of what the bandwidth of a photodiode is. In most cases, electronic receivers will have a narrower bandwidth than the photodetector. So typical systems will take our signal, comes in, it goes into a PIN, but then we'll also put in an electrical filter to limit this wideband noise and only let in an amount of noise which is necessary. And so our electrical filter will have a bandwidth of its own, and this bandwidth will be selected so as to not cut off the signal but to cut off as much noise as possible. So what I would characterize this electrical filter as, we'll just put its impulse response, not impulse, transfer function. We'll call HE of F, the electrical transfer function. And there's a definition, which I guess I'll go into really on Thursday, the formal definition. But for right now, there's a equivalent bandwidth which is a measure of the width of the filter, which is not dependent on the filter shape. So it tries to, although the filter HE of F may have a particular shape in the frequency domain, the equivalent bandwidth, the noise equivalent bandwidth, in fact is what we usually call it, noise equivalent bandwidth, reduces the filter to one characteristic. In this case, the typical system, we would try here, our signal comes in, it's a PIN photodiode, it gets filtered by an electrical filter. We have the received signal, which is continuous, and then we're going to sample it. So this is sampling in order to get a decision statistic, which will be based on signal plus some noise. So after passing through, so this PIN creates thermal noise. The electrical filter limits thermal noise. And now the sampler creates a digital sample, or a single sample, of the continuous time random process, which is additive white Gaussian noise. And all that to say that the noise sample that we see here at the output of our receiver has a variance. So the noise variance of the decision statistic after the sampler is given by sigma squared thermal is just equal to the power spectral density of the thermal noise times the noise equivalent bandwidth of the front end, the electrical front end. What will be, clearly this is Gaussian since the noise is Gaussian and the filter is linear. So we have a linear manipulation of a Gaussian process, so this is also Gaussian. So we would say that the thermal noise has a Gaussian distribution, which is zero mean and has a variance. So this is a notation I will be using. This script n refers to normal or Gaussian. And the first argument is the mean. Second argument is a variance. And the little tilde means is distributed as. We will have a collection of noise samples, one at each one of the sampling intervals. In fact, what we'll be talking about on Thursday is a brief review to remind you that if a Nyquist filter is used, the noise samples will be uncorrelated. And of course, for Gaussian random variables, uncorrelated equals independent, which allows for the bit error rate analysis. Okay, so very straightforward. I'm sure you've seen this all before. Next topic is PIN, but this time shot noise. So I said that PIN creates thermal noise, but it also creates something called shot noise, and which is a little more interesting, actually, than thermal noise. The shot noise has its origin in the fact that the photons arrive with Poisson statistics. And time allowing, I'll get into a little bit of the discussion of this origin on Thursday, although realistically I don't think I'll have much time. It's a white process. So shot noise is a white process. And although if we speak rigorously, it's a Poisson process, in the regimes of operation it is well approximated as Gaussian, again in most telecom systems. So it's a white noise process, well modeled as Gaussian. So far it sounds very similar to the thermal noise, but there's a very important distinction in one way that it's different, and in one way that often distinguishes between radio frequency digital communication systems and optical communication systems is that the noise varies with the input power. The noise power varies with input signal power. So it's knowing that the origin of shot noise is from the Poisson arrival statistics sort of makes sense. The stronger the power of the arrival, the stronger the noise is. So remember, thermal noise is not like that. No matter how strong the signal is, thermal noise is a fundamental limit, not related to the signal strength, whereas shot noise is more severe for larger signals. Now, of course, we're talking about digital communications systems, and of course in digital communications there is the logical 0 and the logical 1, which means that the instantaneous power will be different depending on which data is sent, which means the shot noise power will be different depending on whether a logical 0 is transmitted or a logical 1. For now, let's just consider a continuous wave signal, what the equations are for the shot noise. So we'll think of it in terms of instantaneous power to just keep these ideas clear in our mind. Instantaneous power. So the power spectral density of shot noise is equal to the electron charge Q times the responsivity of the photodiode times the input signal power. So this is the electron charge, responsivity, which is given by, if you want, the efficiency of the PIN times the electron charge divided by Boltzmann's constant and the frequency. And this is the signal power. So right away we can see that what we should be talking about are two different power spectral densities. One is for a logical 0, which would be QRD times the power in a logical 0, and the shot noise for a logical 1, QRD P1. In a perfect optical communication system, of course, P0, there would be, well, I'm going to talk today exclusively about on-off keying. Which is also known as intensity modulation with direct detection. So on-off keying would be the term used for all digital communications. When in particular we use on-off keying in an optical communications system, we typically refer to it as IMDD. So assuming that this is the modulation type we're using, in theory the power on a logical 0 should be 0. But in fact, the optical components that we use lead to a finite extinction ratio so that the power is not completely 0 during the transmission. So whatever that power is, small though it is, there will be some shot noise induced by it. Again, the power spectral density of the shot noise is just flat over all frequencies, or maybe we'll say the bandwidth of the PIN. And so the same as we saw before, the sampled noise, shot noise, has variance. So sampled noise variance is NSN times the noise equivalent bandwidth. In a numerical simulator, how would we go about simulating a PIN? Well, we would start with the input signal in our simulator. We would have to know what the power is in order to be able to calculate what the noise level was. So I'll put a different path here for our simulator. The simulator would certainly simply raise the signal to the squared, and then it would add to it a additive white Gaussian noise which is the shot noise, depending on what the instantaneous power was at the instant. And then it would also add to it an additive white Gaussian noise, which was a thermal noise, which is not signal dependent. And then we would go into our electrical filter and do our sampling. Sometimes what we'll do, in this case, we're generating a random process, which is somewhat more difficult. So often what we'll do in a simulator is we'll do something equivalent. We'll take the signal, we'll square it, we'll filter it, and then what we'll do is we'll sample it, and we'll add noise samples. So instead of adding a random process, we'll add some random variables. So we'll still take knowledge of P in, and this knowledge of P in will calculate a random variable. And typically these will be considered an IID sequence. So they're independent due to the use of a filter, which is Nyquist, and gives us independent noise samples. And one will be for shot noise, and one will be for thermal noise. I'd like to talk to you about how you would predict the bit error rate based on this theory for the PIN. Let's suppose, as I said, that we're using on-off keying or IMDD. Some simplifying assumptions, first of all, when we do our derivation of the BER, and that is that we said we have a perfect monochromatic source. We're not going to worry about relative intensity noise. We're not going to worry about phase noise. So everything is perfect to start with. There's no ASE. So we're just going to look at the simple one. So the system here will have the power during a logical zero would be equal to the extinction ratio times the power for signal 1, and of course it's much smaller than 1. We hope we have a decent extinction ratio. And we're going to let the photocurrents be defined as I0 equal RD times P0, I1 equal RD times P1. Okay, so we're going to add to these currents the noise is added. And again, we said that this is Gaussian. So we're going to talk about the conditional probability density functions. So this is conditional, and this is a PDF. Probability density function is for the photocurrent, which is the sum of both the signal and noise. So the signal is going to be either I0 or I1 during whether the sample is taken during a logical 0, logical 1, and the noise is going to have a Gaussian distribution with 0 mean and sigma squared, which will either be a 0 or a 1. So there are two different variances because there are two different input powers. And so which one should I use? Well, I have to condition on an assumption about which bit is actually being transmitted. I can think of the total bit error rate as being able to write as the probability of sending a 0 times the probability of making an error given that a 0 is sent, plus the probability of sending a 1 times the probability that there was an error when a 1 was sent. So this is the total probability of error. I could have made an error when a 0 was sent. I could have made an error when a 1 is sent. Typically we deal with equiprobable data, so the probability of sending a 0 is 1/2, and we have the probability of error given a 0 plus 1/2 the probability of error given a 1. So these are the conditional probabilities, conditional PDFs that I referred to. So in order to calculate the bit error rate, I have to know what these conditional probabilities are, and I calculate the probabilities from the probability density function. Let's think of, first of all, maybe systems that you've seen typically in a digital communications course. In a digital communications course, typically the additive noise is not signal dependent, it's signal independent, which means it has the same variance for both logical 0 and logical 1. So if we look here, we have the received signal, which is wiggling around 0, jumps up, wiggles around 1, goes down, wiggles around 0. And if we create a histogram, for instance, on a test and measurement device, or if we look at the theoretical conditional distributions, we would get the red and the blue distributions, which are Gaussian with shifted means. So the mean value here would, for the logical 1, would be I1, and then the mean for the logical 0 would be I0. These two different means that these things are centered on. Okay, so that's what maybe you've seen typically. And what we define is where these two Gaussian distributions intersect is where we would set what we call the optimal threshold. If we want this expression for the bit error rate to be as small as possible, I want to balance out the errors that are made when I send a 1 with the errors that are made when I send a 0. And if I want them to be smallest, I will set my threshold so that these two conditional probabilities are equal. So if you look at what's shaded in blue there, it's the errors from, I say BER, I guess I should say it's the errors when the 0 sent. So it's really the conditional BER. And if I looked at this side, it would be when 1 sent. And the sum of 1/2 of one plus 1/2 of the other gives a total bit error rate. And if I want to make that bit error rate as small as possible, what I want to do is to get these two regions to have the same area. And if I have the symmetry like I do in this case, when I have the same variance for both Gaussians, then the decision point, the optimal threshold, I would put at the midpoint, which is where the intersection occurs. So this threshold is what I use to determine whether I think a 0 or a 1 was transmitted. So we see now that the threshold is put in the middle of our timing diagram here to say, if I have a sample here, it will be below the threshold, and when it's below the threshold, I will choose that a 0 was sent. If instead I have a sample that's up here, I'm going to choose that a 1 is sent. Of course, hopefully I'm going to be doing my sampling at the center of the eye, so I'm going to be very here, it's very unambiguous, and I would choose a 1 is sent. But the decision is made based by comparing the decision statistic with this optimal threshold. Okay, well, what happens when we don't have symmetry, when we don't have identical distributions? Noise variance is different. Sigma 0 squared not equal to sigma 1 squared. Well, let's look at this case. So here we have the case of the noise on the 0 level being smaller than the noise on the 1 level. So you see the same shift of means being different, but in addition to the means being different, you can see that the variance is larger on the logical one because the shot noise is stronger because the signal is stronger. What this means is that finding the optimal threshold is not as trivial as it was in the previous case. But what the strategy remains the same. We would like to find a threshold such that the probability of error given a 0 cent is equal to the probability of error given a 1 cent. And that would be the optimal threshold. So how do we find that in this case where these two variances are not the same? And this is a little trickier. When I say that the two areas should be the same, that means that I'm assuming that this is equiprobable data. In order to find what the optimal threshold is, we're going to delve more deeply into the bit error rate probability. So it's 1/2, and I said it was the probability of an error given a 0 cent plus 1/2 probability of error given a 1 cent. And when do we make an error? Well, I already said I'm going to be using some threshold. So I make an error when a 0 is sent. I make an error when the sampled signal, I guess I'll use x for the sampled signal, when x is greater than the threshold, but a 0 was sent. So I made a mistake. A 0 was sent, but somehow the noise was so large that it pushed up the signal plus noise sample x, the decision statistic, above the threshold, and I made an error. And that's the same as 1/2 the probability that x is less than the threshold when a 1 was sent. So now I know that the conditional probabilities are Gaussian. So I'll write that underneath here. This probability density is Gaussian. In this case, the mean is 0 is sent, so the mean is 0. And of course, the variance is sigma 0 squared. In this case, it's Gaussian. The mean is I1, and the variance is sigma 1 squared. So the probability that x is greater than some threshold, and gosh, I hope it's clear, this is an n for normal. This is the threshold, okay? Those are not the same symbols. The probability that I am greater than theta is just theta to infinity, the probability density, and the density here is 1/2 pi square root of sigma 0 squared, and then e to the minus x minus I0 squared to sigma 0 squared dx, etc. And here it will be from minus infinity to theta 1/2 pi sigma 1 e to the minus x minus I1 squared to sigma 1 squared dx. Theta optimal, how would I find it? For equiprobable data, I would like these two equations to be equal. These two representations of the Gaussian. So this happens at the intersection. So let's look back at our graphic here. We have equal probabilities if we find the intersection of these two probabilities. So if I want to find the intersection of them, I look at the probability density functions, which are written in here, and I try to put them equal. So I'm saying the optimal occurs when they coincide. So then the optimal one minus I0 squared over 2 sigma 0 squared would equal, well, I1 minus the optimal squared to sigma 1 squared plus the logarithm of sigma 1 over sigma 0. So I just took the logarithm of both sides to come up with this expression, so I didn't have the exponential in it. Note that when sigma 1 equals sigma 0, the logarithm is 0, and I get a simple expression where the optimal theta is the midpoint between I0 and I1. At the midpoint, that happens in this case just by the symmetry. But in this case, with sigma 1 is not equal to sigma 0, this is not necessarily the case. So finding a solution to this expression in closed form is difficult because of the logarithm. So now we'll make one of our simplifying assumptions. And that is that the logarithm can be neglected. Now, in this case, it still will not be the midpoint because the midpoint was also due to the denominators being equal, that symmetry, which will not be the case now. So we're still going to neglect the logarithm, won't be 0, but we're going to keep sigma 1 not equal to sigma 0. And this is, given that the logarithm is a very slowly growing function, this is a good approximation. So the we'll say the quasi-optimal threshold, in this case, occurs at minus I0 squared to sigma 0 squared I1 minus optical squared. Of course, we could take the square root of both sides, so let me just do that right away. And the 2 will cancel on both sides. So I get something like this. And this is quite easy to solve. And when I solve this, I get that the optimal threshold is sigma 0 I1 plus sigma 1 I0 over sigma 0 plus sigma 1. So one of the things that you'll be exploring in your validation is use of the optimal threshold. And one thing you'll find is that you really shouldn't use the optimal threshold because the optimal threshold will not actually give you the minimum bit error rate because of various imperfections in your simulator, the finite bandwidth of your simulator, many factors. So what will be, when you get the MATLAB code for the homework, what you'll find is that we use the theoretical threshold as a starting point, but that we actually use a numerical technique to find the optimal threshold. And in the homework, we'll try and develop what would be some of the reasons that this might be the case. But certainly this is the theoretical version. And what I'd like to say is also, if we take a step back and we go back to this equation, I'm just going to take n op minus I0 over sigma 0, and I'm actually going to plug in what we have found to be the optimal threshold. So we'll do I1 minus eta optimal over sigma 1, and then I'll say that that's I1 minus sigma 0 I1, sigma 1 I0, sigma 0 plus sigma 1, all divided by sigma 1, which is the same as sigma 0 I1, sigma 1 I1, minus sigma 0 I1, minus sigma 1 I0, all divided by sigma 1 plus sigma 0. And of course I have these terms that cancel, and in the end this becomes, well, this cancels with that. And what I get in the end is something quite simple. It's I1 minus I0 over sigma 1 plus sigma 0. And this I will define as something we call the Q factor. So we can say that at the point of intersection, we would have E to the minus, and it's x minus the mean divided by the variance, that this would equal e to the minus q squared in both cases. So at the point of intersection, we have this result. And of course, this Q factor, it can be useful when we're calculating what is the bit error rate. So we found the optimal threshold. Now we want to use it to find out what is the probability of error, for instance, giving a 0 is sent. It would be 1 over the square root of 2 pi sigma 0 minus, it's actually eta to infinity. And this is a 1. Okay. 1 minus infinity to the eta optimal e to the minus x minus I1 2 sigma 1 dx, which if we use the error function is equal to 1/2 the error function of eta minus I1 over the square root of 2 sigma 1. And again, the definition of the error function complementary, sorry, I need the C there, is 2 over the square root of pi, x to infinity. This is the definition used in MATLAB. Y. Okay, so the nice thing is that if we take this expression, that we can simplify this and say that it's just equal to 1/2 the error function complementary for q over the square root of 2. So q clearly is a useful parameter in characterizing the bit error rate performance, and it's a very trivial exercise to show that this is also equal to the probability of error when a 0 is sent, and that the total BER then is equal to 1/2 error function complementary q square root of 2. And if we interpret the q function, we can see that this q function has the characteristics of a signal-to-noise ratio, because we have the separation of the two signals in the numerator. So the farther apart the signals are, the larger the signal power for discerning between the two. And in the numerator is the noise, sort of combined noise for the logical 0 and logical 1. So this Q factor makes a lot of sense as a measure of quality. And I just want to mention one useful approximation, just numerically. If you've got a calculator, you're trying to do some calculations, you don't have MATLAB, maybe you don't have the error function complementary available, the bit error rate is very well approximated as e to the minus q squared over 2 divided by q square root of 2 pi. So that's just an approximation for the complementary error function. Move on now to the next topic, which is amplified spontaneous emission. Now we have a nice theoretical equation for what happens on the sources of noise due entirely to the PIN, and now I'd like to look at optical amplification. So typically we refer to this as ASE, amplified spontaneous emission. So an optical signal which undergoes amplification sees a gain of G, and it has a noise process created so that the output of the signal S goes in. We have some amplifier, let's say an EDFA. What comes out is something that is G, the gain, times the input signal, plus a noise process, an additive white Gaussian noise process. Very wide band. And the noise process will be much, much wider band than the signal process. So of course, because it's so much wider band, then what we're going to want to do is limit it. So we'll have in a typical system that sees an optical amplifier, and that could be a SOA as well. We'll put an optical filter to limit the impact of that process. Then we'll go through the photodetection, and of course the photodetector also adds wideband noise, and so we're putting here an electrical filter in order to limit the effects of the electrical noises introduced by the optoelectric conversion. So the optical filter has wide enough bandwidth to pass the signal without distorting it, but narrow enough to limit the noise as much as possible. And the same thing is true of the electrical filter, but of course the optical, well, let's go into the mathematical description of what we see going on here. So what happens when I have a signal plus a noise process that goes into the photodetector? So now the photodiode produces photocurrent proportional to the square of the sum of the filtered signal and the ASE field. So we see that what's going in here to the photodetector is now G times S of t plus this noise process. And so on the other side, of course, we'll get the square of this entire field, which means that the shot noise will be higher, will be enhanced by the presence of ASE. This is one of the main reasons why we put in this optical filter, so that we could reduce the amount of power incident on the photodiode to keep it as small as possible. The square law is also going to create beat terms in the photocurrent. So what happens here is we have, we have G S of t plus N S P, right, squared, and that's going to give us G squared S squared, oh boy, this is not very good handwriting, G squared S squared of t plus 2G S of t and spontaneous emission of t plus NSP squared of t. So everything that I'm describing today can be seen discussed in the Olson paper in Appendix A. The vocabulary we use is that this is the signal spontaneous beating, or the signal ASE beating, and this is the spontaneous beating term, or the ASE beating term. So in the Olson paper, in Appendix A, there's an analysis where we assume that the ASE noise is a collection of narrowband signals. So although ASE is a very, very wideband noise, we assume it's a collection of a bunch of narrowband signals, each of which has a random phase and constant amplitude. Because it's a thermal noise process, it's got random phase, constant amplitude, and in the analysis in that paper, they let the bandwidth go to 0, so that each one is very, very narrow band, and the number of components goes to infinity. And in that analysis, I'll just give you the results of it. So they find this analysis gives the power spectral density of the signal spontaneous and the spontaneous beating terms. So I refer you to that paper if you're interested in the details. Right now I'll just give you the results. So the signal spontaneous term. In this case, we get a flat PSD whose height is proportional to 4 times the photocurrent induced by the signal times the photocurrent induced by the spontaneous emission divided by B0. So that's the level of the power spectral density centered on the optical frequency from minus with a total bandwidth of B0. So it's as wide as the optical signal bandwidth centered at the carrier frequency for the signal, and the photocurrent signal-induced photocurrent is given by RD times G times the power of the signal. And the spontaneous is the ASE-induced photocurrent. And that is equal to Q N FP G minus 1 B0, which we can also call RD times the power of the ASE. In the homework, I guess I should specify that this quantity altogether is taken to be minus 35 dBm per 0.1 nanometer. So this assumes that the ASE is essentially flat power spectral density, and it's multiplied by the bandwidth of the optical signal. You could also consider this to just be the power of the ASE as it comes out of the filter. So it comes out to be the same characterization. So let me just get rid of that now. And instead, what it refers to is this as S ASE of F times BO. So the power is both of these, and this refers to the power spectral density. NSP is a characteristic of the amplifier. It's typically in a range from 1.4 to 4. For our purposes, we're going to use some very simple characterization of the ASE noise. So returning now to the other term, which would be the spontaneous beating term. This one has a power spectral density, which is triangular, symmetric in shape, going from B0, minus B0 to B0, so a total width, absolute width of 2B0. And the height of this triangle is 2 ISP squared divided by the optical bandwidth. And we've already defined all these. So these spectrums represent the noise due to ASE, which is out at the output of the PIN. So if we look back here to our system, now we've got equations for the power spectral density here for all the terms. We know the power spectral density of the signal is whatever it is, and now these noise terms that we've added, and of course there'll also be the thermal noise and the spontaneous noise. But now what happens when we apply an electrical filter to these noise processes? So let's start by let BE be what I called earlier the noise equivalent bandwidth of the electrical filter. Clearly for the signal spontaneous noise, the noise variance becomes the integral of the signal spontaneous power spectral density times the module squared of the frequency response of the electrical filter. Now I plug in the square filter shape that I have for the signal spontaneous, and then what I get is minus B0 over 2 to B0 over 2 for ISP, B0, and I have HE of F squared dF. And these are constants, so the constant terms can be brought outside the integral. And so what I'm left with is that the signal spontaneous variance squared is equal to 4 ISP over B0. And here I have minus B0 over 2, B0 over 2, HE F dF. And this should be equal to approximately equal to simply BE. So if B0 is much greater than BE, then it's essentially minus infinity to infinity, and it's the equivalent of the definition of the noise equivalent bandwidth. So now I finally got into the definition of what the noise equivalent bandwidth is. So in this case, we see that this simplifies to signal spontaneous is just equal to 4 ISP B0 times BE. If we look at the case of the spontaneous, it's a little more complicated. Let's see if I can draw it for you here. I had this power spectral density that went from minus B0 to plus B0, and now I'm thinking in terms of a square electrical filter as an approximation. So now I'm filtering this power spectral density so that there's two portions, right? There's the portion in here that we're going to use as the approximation of noise variance. I probably should really include this little cap, but you know, the BO is so much bigger than BE that doesn't make much difference. And now I just want to calculate, you know, what is this area. The noise variance is approximately equal to the area of this rectangle. And so it's easy to find the expression for the area. Certainly this width is clearly B0. And to find out this height, well, we just start from, we know the height here is 2 ISP squared over B0. And then we can take the slope of this line, find out what the height is. Anyway, we come out with this sigma squared SP is equal to BE times the height of that rectangle, which turns out to be 2 ISP squared BE over B0 squared times B0 minus BE over 2, which we can write as ISP squared BE over B0 squared 2B0 minus BE. So, to summarize, now we've got all the components we need of calculating the total noise and signal process at the output of the sampler. So we have noise, all noise contributions. So once again, I0 is equal to the input power, G times P0, times RD. And this is, we could also write this as R times the extinction ratio times P1, RD. Sigma 0 squared. So the noise variance when a 0 is transmitted would be the thermal noise, plus the shot noise when a 0 is sent, plus the signal spontaneous noise, plus the spontaneous noise, which we found these equations for previously. And recall, be careful, calculated for power in of G P0 plus PASE. So the ASE power will also increase. And of course, if I have a logical 1, very similar, but now I have, of course, all these expressions are changing because the P1 instead of P0. But again, the shot noise has power in of G P1 plus PASE. So we can now see that the shot noise is actually getting closer in value between the cases of 0 and 1 because we have this ASE common term in between the two of them. So in some respects, we can see that the sigma 0 squared and sigma 1 squared are somehow getting closer when we include amplified spontaneous emission. Okay, so this gives you the theory you need in order to accomplish the homework. As I said, I have a half-hour recording. Think of it as a problem session where I explain some of the homework to you. But in the last 10 minutes of the class, I'll just give you an overview of what the homework is involved. So it's very much the systems that we've been discussing so far. I've done a little sketch here of, it's first of all in the homework, it's all MATLAB because I want you to see what's going on underneath, if you will, everything that's going on in OptiSystem. So it'll give you an appreciation of the validation. So this is all about validating theory, and for that you have to have somewhat more control, and it's also something you could do for your OptiSystem down basics. So anyway, we start MATLAB, but it's not a coding class, so I give you as much as I can of the code already. And in that code, if you look over it, what we see is we have a very idealized laser. So there's no phase noise, there's no RIN noise, it's just a perfect monochromatic source. One thing I do add to it that we'll be discussing next on Thursday is to give a pulse shape to the signal. So it's not just a necessarily a rectangular shape. We'll talk about other shapes which may be more desirable. And the external modulator we use, an ideal external modulator. I think there is a way of manipulating at least the extinction ratio, but I think the extinction ratio in the homework is very, very high, so there's not much effect due to a non-ideal external modulator. We have an ideal fiber. Again, it's just a zero dispersion. It simply introduces attenuation. So we have an optical filter. For the optical filter, the shape that we've selected is a super Gaussian filter. Again, the code is provided for you there, and we'll be specifying what the optical bandwidth is. We'll be varying that in the homework. The PIN diode is implemented as a square law detector with thermal noise and shot noise added. And of course, in your MATLAB code, we're adding the thermal noise and the shot noise, and we want to make sure that we're adding it in the correct way. So one of the things that we'll be validating is using the MATLAB code to run a Monte Carlo simulation of what the noise component is, and then you'll be plotting also a theoretical calculation of what the bit error rate is for these thermal and shot noise levels you've set, so that you can make sure that your code is properly run. And I'll tell you, the focus, I say I provide 90% of the code, and you're missing 10% of the code, and the 10% you're missing is about normalizing signal-to-noise ratio. And it's the largest source of confusion that I've seen with my students is how to correctly normalize the noise so that you can correctly interpret your results. So that's sort of the validation is focusing on that error, which I think happens quite frequently. So the electrical filter will filter this noise, and we're going to be also playing in the homework with different pulse shapes and different filter shapes on the electrical filter. So that's one of the things that we'll be varying in the main part of the homework set. Afterwards, we do a sampling at the symbol rate and then a threshold detection. As I mentioned, you'll be in the MATLAB code. They'll be calculating bit error rate with the optimal theoretical threshold and then comparing it with a numerically optimized threshold. That's one without ASE, and then we'll also be running the same experiments with ASE added. So you can see here there's optical amplification, there's a perfect gain, and then there's the ASE process. So there are the two aspects that will be examined. This is supposed to be, you'll only be generating one wavelength. However, the equations we develop are also applicable to WDM systems because we are using an optical filter, so that optical filter could be used to isolate the channel, reduce the crosstalk, and in that case the equations that we have should be valid for even a WDM system. Again, this is all done in MATLAB. If you're interested in also comparing it with OptiSystem, that would be great. I don't require that for the homework. Anybody does it, I'll be happy to have a look at it. They should give the same results. Like I said, I just want to get under the hood a little more about the normalization to make sure it's being done correctly, but this is a valid point even with OptiSystem. So we're going to be assuming 50 gigahertz spacing on these WDM channels, which means essentially that we're setting the optical bandwidth of our filter. So our optical bandwidth of our filter is going to determine the level of ASE.